Hello everyone, my name is Nikhil Best and I'm a mechanical engineering student at NIT Jalandhar. This is my video submission for the Altair Optimization Contest. In this video, I'm going to walk you through the complete engineering workflow of my project, how I designed, analyzed, and optimized a complete 3D printed robotic arm using Solid Edge and Altair Inspire. So yeah, let's begin. Okay, so I started with modeling in Solid Edge. You can see here. The one thing which I really liked about Solid Edge was its integration with AI. So basically what it did was it kept on suggesting me the most probable next feature which I would use to create the part. So whenever I was doing modeling, the next feature was right on the bar and that saved quite a lot of time for me. You can see here the model. It has 6 degrees of freedom and it uses 6 motors. One at the base, three at the links, and two at the grippers. So the next I exported this as an IGES file to the Altair file. So yeah, moving on. Okay, so you can see here the model has been imported in Altair Inspire. So I began with defining my grounds. The platform and the base of the model are ground, so they are removable. The next is I define joints. You can simply click find and it will automatically detect where the joints can be placed in the model. And by clicking on them, you can define whether it could be a hinge, a cylinder, or pane, or etc. Right? So that is quite easy to do. The next is the rigid groups. Okay, why do we need that? Sometimes what happens with us is that we create a new part instead of combining it to the previous. You can see this was created as a new, but it was supposed to be together, right? So simply using rigid groups, you can combine them, and they now will behave as a single rigid group. The next, I define context, how two parts interact between them. Like see this block over here. If I do not define the context between the platform and the piece of block, it would simply pass right through it. So we don't want that, right? And this feature helps to build the physics. That is quite useful. Okay, the next I have defined motors. I have defined 6 motors, one at the base, three at the links, and two at the grippers. So you can define motors in a lot of ways using angular acceleration, velocity, torque, or angle. I have defined them using angle. In what time, how much angle the motor rotates. There are a lot of functions to find the angle curve. I have used a table. You can see between 2 to 3 seconds it moves 45 degree. So that is how all the motors have been defined. I'll show you the simulation, the motion analysis. So yeah, you can see this is a real life situation of how the robot arm performs. It picks that block and puts it right into the destination bucket. Meanwhile, and you can track the real time torque which is being applied by the motor. This curve over here. You can see for this motor, around 5 Newton meter of the max torque is being applied. Similarly, for this motor as well, this gives me an idea of how the Robotom will perform in real life, and I can use these values to perform a better structural analysis. Okay, and also I have defined gravity in the downward direction. Okay, moving on to the structural analysis, you can see here I have isolated the link to which is our target to analyze and optimize. So for the analysis, I have applied two torques. Uh, the one on the below it is 30 Newton meter, and the one above is 5 Newton meter, which I got from the motion analysis. And I also have applied a support roller support, which doesn't make the part to float freely in their space. So we are good to go with the analysis. I'll show you the results. So you can see here the one misses stress. The blue region means it is very safe, and it also means that there is a huge scope of improvement in these areas. So the next we have a lot of results. The displacement, how the part is moving. There is an animation as well. You see, this is scaled, so actually it is not moving that much. It is scaled by 2000, so that's a lot. The next is factor of safety. So we have got a minimum factor of safety as 182, which is quite a lot, right? We usually don't require that much. So it tells us that there is a huge scope of improvement. So after this, we move on to the optimization part. So for that, we need to assign design space. Okay, the area which we need to change. So also we need to define areas which we do not want to change, right? For the area where it will connect to the other parts. For that, I have used the partition tool and created these rings. These are the places which should stay intact, so I can connect them to the other parts, right? And then assign this as a design space. Also, we need to define we can define shape controls. It means if there is a symmetric part, if there is a plane along which we want our part to stay symmetric, so it will tell the software to stay symmetric about that. Okay. So you see here there are three planes, but I will deselect it. Okay. Sorry. Okay. So this uh, I will deselect this one and this one. So I want it to be symmetric in this plane, right? So yeah, we are good to go with the uh, optimization. Our target, okay, sorry. Our target is to minimize the mass, and we need a minimum factor of safety as 6. The other things are assigned by the software. And when you run this thing, you'll get the results. And this is what the software gave us. You see, a lot of blue area is now removed, which was experiencing low loads, and we don't need that, right? So this is quite efficient. But you see here, the geometry is quite rough. It is very inconvenient for us to print this thing, right? For this, the Altair gives us a tool. What it does is it smoothen out the geometry. So you can do it either automatically or you can do it manually as well. So first I'll show you the result by the software, right? And one thing which I really like about Altair is how it has unified everything into a single workspace. You could do the motion analysis, structure, geometry, and everything, and it is all here in a single software. So that is quite a thing, and kudos to the Altair team. So yeah, you see here, this one is the organic shape. You see, it is very smooth. It is very easy to print, and this gives us a very optimized part. So I'll show you the result. I'll show you the weight of this thing. And for the context, the part initially weighted around 0.541 kg, and now and yeah, it's like this because wait, now it is 0.185 kg. This must be something some few grams. So approx 0.1195 1.19 kg, which is like a huge improvement, right? More than I'd guess 60 to 70% mass has been reduced. So yeah, the next I thought about doing some PolyNURBS manually. So like there are a lot of features, fit, wrap, wave, and you could change it according to you. Altair gives us full control over our part. Like I use my engineering logic. Like there would be need of some branches, though it is not required. This part is sufficient as well. It is properly able to withstand what we assigned it the loads. But I thought to play around with software, and you could do it as well. So I created, I used this pave tool to create some area over here and to connect it with this branch. I'll show you the results. Okay, so you can see here I have manually done the polyNURB tool and you can see it looks really good. Okay, I should suppress. So this is what I have got. It is quite a good improvement, I would say. This part now, wait, okay. This part now, the weight is a bit increased. Maybe a bit. This one, this one, and this one. Like, so the part weighs around 0.141 kg. Oh, I reduced the mass as well. The branches were thinned out. You can see here. So that gives us another improvement as well. So down this part it looks really good. I'll show you how it now behaves with the part. The robotic arm, complete robotic arm. So yeah. Okay, so this is the final motion analysis. You can see here our part. It is looking really good. And one thing which I would like to tell you is if you are doing structure and motion together, you should suppress the loads of one to do the other, right? It took me quite few hours to figure it out. I was not getting what the thing I was doing wrong, and you should suppress these torque and support for the motion to get right. So, yeah. And now this is the final motion. You can see the robot arm is moving perfectly fine. And to me, it looks like really good. It would be really fun to print this thing and see how it behaves. So yeah, that's it. Thank you for the Altair team. They are providing OptiStruct for free. The interface is really good. There are a lot of good features, especially the PolyNURBS, the very smooth geometry you are getting. And the Solid Edge Solid Edge CAD was like really good. The AI integration thing is quite cool. So yeah, thank you for the license. I hope you liked the video. Thanks for watching.